Hello everybody. Let's discuss a question on quadratic equations. We're given two quadratic equations a1 x squared plus b1x plus c1 equal to 0 with roots alpha 1 and beta 1. And the second equation is alpha 2 x squared plus beta 2x plus c2 equal to 0 which has roots alpha 2 and beta 2. And we're also given that this determinant is 0. Now, under this condition, we must show that this thing will always hold. So first of all, let's look at this. Alpha 1 plus beta 1, the sum of roots of the first equation, will be equal to negative of the coefficient of x1, the coefficient of x, which is b1, and over the coefficient of x squared, which is a1. And similarly, alpha 2 plus beta 2 will be equal to minus b2 over a2. Let's call both of these equations as equation 1. The product of roots alpha 1 beta 1 will be equal to the constant term over the coefficient of x squared, which is c2 over a2, and we also have for the second equation alpha 2, this is c2 over c1 over a1, okay, c1 over a1. So alpha 2 beta 2 will be equal to c2 over a2. Let's call it 2. Now let's evaluate the determinant. We're going to get alpha 1 beta 2 to be minus alpha 2 beta 1 to be equal to 0. So basically these two quantities, they are equal. So let's call it number 3. Okay. Now to prove this, I prove this equation for under the given conditions. We consider two cases. Okay. The first case is that at least one of alpha 1 beta 1 alpha 2 beta 2 is 0. Okay. And the second condition, second possible case is that none of them is 0. Alpha 1 beta 1 alpha 2 beta 2 not equal to 0. All right, these two cases. Let's consider the first case for now. Okay, let's consider the first case. Then at least one of them is 0, so we can take any one of them to be 0. Okay, it's your choice. I'm gonna take alpha 1 equal to 0, and if alpha 1 is equal to 0, you can take beta 1 equal to 0, alpha 2 equal to 0, or beta 2 equal to 0. We're going to get the same conclusion. Okay, we're going to reach at the same conclusion. Okay, you can try it yourself. I'm going to take alpha 1 equal to 0. All right. Okay, if we take alpha 1 equal to 0, then from this part of the equation 2, we're going to get c1 is equal to 0. Okay, we're going to get c1 equal to 0 because c1 over a1 is equal to beta 1 times 0. So this will always hold. And next, if we take this equation 3, then alpha 2 beta 1 is equal to alpha 1 beta 2, and alpha 1 is 0. So alpha 1 is 0 means the product is 0. So from here we can say that either alpha 2 is equal to 0 or beta 1 is equal to 0. Okay, so under case 1 we have two subcases. The first subcase is alpha 2 equal to 0. If alpha 2 is equal to 0, let's see what happens. If alpha 2 is equal to 0, then from this part of the equation, this part of equation 2, we're going to get c2 equal to 0. And now left hand side is equal to a1 b2 squared c1, which is equal to 0 because c1 is equal to 0. And right hand side is equal to a2 b1 squared c2, and this is also 0 because c2 is equal to 0. Okay, so the identity holds. The equation is true in the first subcase. Now for the second subcase, if beta 1 is equal to 0, then now we cannot use these equations because they do not involve beta 1. Now we've used this one, we've used this one, so there's only one equation left, which is this equation, the first part of equation 1. So according to first part of equation 1, we have minus b1 over a1 is equal to alpha 1, which we have already taken to be 0, plus beta 1, which according to the subcase is again 0. So from here we get b1 is equal to 0, and therefore LHS is 0 because c1 is equal to 0, and RHS this time is again 0, but not because c2 is equal to 0. We don't know if c2 is equal to 0 or not, but b1 is 0. So because b1 is 0, RHS is again 0. So under both subcases, this is true. For both subcases, what we have to show is true. So in the first case, for the first case, this relation will hold. Okay, so now it remains to prove that it will hold in the second case also. So let's look at that. Now this part will be slightly tricky. All right, case 2, and in this case we're going to take alpha 1 not equal to 0, beta 1 not equal to 0, alpha 2 is not equal to 0, and beta 2 is not equal to 0. So we can divide by any of these whenever we want. Now in this case, let's see, left hand side is equal to a1 times b2 squared times c1, right? Okay, now let's see, we need a2 on the right hand side. We need a2 on the right hand side. So let's multiply this by a2 times a1 b2 squared c1, but we have multiplied by a2, so we're going to have to divide it by a2 again. Now b2 over a2, there's something here related to b2 over a2, which is this equation. All right, this equation. But let's see, one of them is squared, the other one is not squared. Okay, one of them is squared but the other one is not squared. So let's use a2 squared instead of just a2, in the hope that we can cancel out one of the a2's later on. Okay, we will cancel that. All right, so basically now let's not change this part, let's just look at this part. Okay, so a2 squared times a1 times b2 over a2 squared means, from this relation, alpha 2 plus beta 2 squared. So this is basically alpha 2 plus beta 2 squared times c1 as it is. Now let's take beta 2 out of this expression. Then since we have a square term over here, we're going to get beta 2 squared if we take beta 2 out of this expression, and we're going to get 1 plus alpha 2 over beta 2. All right, and c1 as it is. Now let's look at this equation now. Equation 3. Alpha 1 beta 2 is equal to alpha 2 beta 1. Right? Now let's take beta 1 over here and beta 2 over here. We're going to get alpha 1 over beta 1 is equal to alpha 2 over beta 2. So we can write this as a2 squared a1 b2 beta 2 squared 1 plus alpha 1 over beta 1 whole squared times c1. Alright? Times c1. Now let's simplify this part of the equation, this part of the expression again. Okay? What are we going to get? a2 squared a1 beta 2 squared times, if we simplify the expression inside the parenthesis, we're going to get alpha 1 plus beta 1 whole squared over, what is this? Beta 1 squared times c1. Alright. So a2 squared a1 beta 2 squared alpha 1 plus beta 1 means b1 minus b1 by a1. So squaring this will give, let's take this over here first. Now squaring this will give us b1 squared over a1 squared. Alright, b1 squared over a1 squared times c1. So we can cancel out one of the a1s like this. Alright, now we've obtained b1 squared just like we needed. Okay, a2 squared b1 squared b2 squared over b1 squared times c and over a1 as well, right? c1 over a1. All right. Okay. Now our work will be complete if we can show that this part over here is equal to, what was that? c2. Okay, c2, which is, by which I mean a2 times b2 squared over b1 squared times c1 over a1 is equal to c2. If you can show that, then it will complete our proof. Okay, for that, let's again look at this equation. Equation 3, and let's see alpha 1. Let's take alpha 2 over here and beta 2 over here. Then we are going to get alpha 1 over alpha 2 is equal to beta 1 over beta 2. All right. So if we divide this equation by this equation, what are we going to get? So alpha 2 by beta 2 over alpha 1 by beta 1. The division is allowed because in this case we're considering alpha 1, beta 1, alpha 2, beta 2, none of them to be 0. Okay, so this division is allowed, is equal to c2 over a2 times c1 over a1. All right. Now let's keep it as it is, and from this part, from this equation, we can say that these two are equal. So we're going to get beta 2 squared over beta 1 squared, and if we take this part to the left, c1 over a1 is equal to c2 by a2. All right. Now if we take a2 to this side, then we're going to get a2 beta 2 squared over beta 1 squared c1 over a1 is equal to c2. So whatever we've encircled, a2 times beta 2 squared over beta 1 squared times c1 over a1 is equal to c2. So we've obtained a2, all right, b1 squared, and this whole encircled part is found to be equal to c2. Okay, c2, which is equal to RHS, and therefore our proof is complete. Okay, all right, thank you very much.